Example 3. A compound contains 66.65% carbon, 7.990% hydrogen, and 25.37% oxygen by mass. Please determine the imperial formula of the compound. First, we will summarize the most important information. Numbers with units and what we are looking for are considered as the most important information. If there is a chemical reaction, a balanced chemical equation is also considered as the most important information. You may have already noticed I assign a symbol to every number with a unit. But these three numbers do not have a unit because they are the percentage of mass. To assign an appropriate symbol to the numbers with units, it will help us to find the equation to use because all equations contain symbols, not numbers. Next, we will conduct some analysis to see how we can find a solution for this problem. First, we need to refine our goal. In this problem, we are looking for the imperial formula of a compound. We need to refine this goal to see what kind of calculations we need. When we read the problem, we know that the compound contains carbon, hydrogen, and oxygen. To find the imperial formula of the compound, it's equivalent to say we need to know the values of X, Y, and Z. X, Y, and Z are the smallest whole number moles of carbon, hydrogen, and oxygen, respectively. Then, let's look at what we have. We are provided the percentage of mass of each element. Let's look at the definition of the mass percentage. The three-line symbol represents this is the definition. From the three definitions, we can find the gram of carbon, gram of hydrogen, and gram of oxygen. We know that we're looking for the moles of each element. If you remember, we can convert gram of each element to moles of each element by using the atomic mass. However, when we look at this problem, we know the percentage of mass of each element, but we don't know the gram of the sample. But remember, if you have 100 grams of water, the molecular formula and the imperial formula of water is H2O. If you have 1,000 grams of water, the molecular formula and the imperial formula is also H2O, which means it does not matter how many grams of sample we have, the imperial formula will be the same. This means we can assume whatever gram of sample we have, we still have the same answer at the end. From the definition here, if we assume we have 100 grams of sample, the calculation will be very, very easy. You do not even need a calculator. If we assume we have 100 grams of sample, we can plug the value here. Here, we are given the value of the percentage of mass of carbon. We can calculate the gram of carbon. As I just mentioned, we can convert gram of carbon to moles of carbon. Similarly, we can calculate moles of hydrogen and the moles of oxygen. As we calculate the moles of carbon, the moles of hydrogen, and the moles of oxygen, we can find the smallest whole number moles of each element. At first, this map looks a little messy. Let me tell you the trick how to use this map. You always start from something there's no arrow pointing to as the first step. Then you will follow the arrows here and here, and then this is our next calculation. We will follow the arrow. This is third step. We cannot continue with this path because this requires us to know the mole of carbon, the mole of hydrogen, and the mole of oxygen at the same time. We go back to the beginning. We put the number here, and then this will be our next calculation. Will be our step 4, step 5, step 6, step 7, and step 8. Now let me show you the work, the details of all steps. Step 4 is very similar to step 2. Step 5 is very similar to step 3. Step 6 is very similar to step 2. Step 7 is very similar to step 3. If you know the moles of each element, you can find the smallest whole number moles of each element. This will be our final answer. At the end, I want to emphasize, this is all I need during exam or a quiz. You do not need to show me this map. Can you follow my example to work out this problem by yourself? Can you follow my example to work out this problem by yourself?